Thank you. I want to thank Professor Zuazua for the very kind invitation. It's my first time here in a place as pretty and tranquil and with such rich history. So I'm very happy to be here. So yes, this is the title of my talk. You can see some of the, buzzword. Like I apologize if that they don't mean anything, but scientific discovery, what do we mean, and digital twins, or maybe some of you have heard it. It's a buzzword that's very, very hot, whatever that means in the US at least. So I will try to draw some connection with this, but primarily we use this as motivation because these are things practitioners care. People in industry care, and there are some things that we could do in math department, maybe provide some kind of contributions. That's part of our work. So let me first acknowledge all the people who have contributed. This is just all the former and current group members who have contributed at least one paper to the things I will discuss today. It's, as you will see, it's several years of development and took quite a collective effort to get some of the modest results we have. I would also acknowledge this more recent, the major funding behind this work is this funded by the U.S. Air Force Office of Scientific Research by Dr. Fariba Farouk, on this so-called MURI, Multidisciplinary University Research Initiative. This is a collaborative effort. The PI is Daniel Tartakovsky from Stanford, and then a group of experimentalists and computational scientists. We work together on the topic of so-called mathematics of digital twins. All right, so let me first give you just the motivation. We don't do any of this. This is just, just to show what potential impact this may have. So as I said, the digital twin has been a very hot word. In fact, I believe even in Europe, more than 10 years ago, somebody have told me, you should look into digital twin. That was exactly 13 years ago. Some people told me, I did not pay attention, but now it became a thing. So the idea of digital twin is that it's a digital replica of a physical twin. So this is where the major difference between modeling. So one of the common question one has is that when you talk about digital twin, what is the difference between modeling? I mean, that's what we do every day, which was exactly the question I asked when I first heard of this. So after reading more and realize it's not the modeling we do on a daily basis, which is more generic modeling for a system. This is very specific. So there is a physical thing, and your model is very specific to this particular physical. So it's not just CFD for fluids in general. You're talking about CFD for this particular aircraft. And with this particular configuration, the material, the load, everything is very specific. In order for this to be reality, there has to be a very important bidirectional data exchange. That is, from a physical entity to your digital copy model. Your digital model has to be a real-time reflection of the physical twin. So which means your data has to flow from physical to digital to accomplish synchronization of your digital twin and to update it. And at the same time, having this model, the goal is to realize real-time control, optimization, or decision-making on the physical system. And that requires you to have your data to flow from the digital model, because now you have a model, you can play all kinds of computer games without any real-world consequences, without catastrophic consequences. But you can play this game, predict, and acquire all the evidence so that when real situation happens, you know how to react. And that requires to react in real time so that we can send command to the physical twin to realize this real-time control thing. So anyway, there has been a lot of discussion. I put this National Academy of Science report back in 2024, led by Karen Wilcox from the University of Texas in Austin. It has basically summarized all the state of art of digital twins and the opportunity, the challenges. It's a free report to read. I do caution it's more than 200 pages. Right, so anyway, so what's the major difference? Like I'm having this graph here to again illustrate the important that your digital twin is not a modeling for a certain class of phenomenon. It's not a modeling for a certain class of equation. It's for a very specific thing. As you evolve in real time, so what we usually do, our work usually stays here. We are doing some kind of prototyping. We're simulating something, create a model for something, and we don't really worry about the rest of it. This is what industry people dealing with real-world problem, they care. That's the real-time control and how to use your digital model to guide the decision-making for the physical twin. It requires many, many tasks. And all these things, I have a very short list of the important things that in order to realize this very simple diagram, and you look at these things, there's nothing new here. It's something we, in computational math or computational engineer, we do every day. Anybody has worked on one or more than one area at some point in his or her career. So there's really nothing new. The new thing is that you have to put this all together such that it's become a real-time thing. And that's where the challenge is. To me, I would like to emphasize the biggest challenge here is this model, because for complex system, a model, numerical model, can be very expensive to simulate. On a parallel computer with massive number of CPU and GPUs, it may take you a week to simulate one scenario. And how can you simulate, then do control decision-making in real time? That's a real challenge. To make things even more challenging, many of these tasks, inverse problem, UQ, data simulation, in fact, requires repetitiveness, more than once, 100 times a simulation of your forward problem solver. So that makes just more than one simulation. This is even more challenging. So this is where the challenge is. There are many challenges. This is one of the biggest ones in my view. And this is where we try to come into maybe try to do something here on a, at least more or less speaking on a fundamental level to try to speed things up. I mean, of course, you may have heard that many techniques, depending on the system, you can try to speed things up. Most notably, reduce order modeling. You can try to reduce your system to a smaller size by sacrificing certain accuracy. But at the end of the day, how much can you reduce? And for a big system, even your reduced order model can be expensive. So there's a limitation for everything. So what we want to discuss is that let's focus not on the full system. Imagine you have a massive system, that's digital twin, it's just a model, right? Governed by coupled PDEs, ODE, algebraic, whatever conditions. At the end of the day, I see a model is a time stepper. It's a very expensive time stepper. So like this, knowing the current time is Markovian process, we'll try to predict the next time, what the state variable. I put a very long vector here, just say this state vector can be very big, because after finite element discretization, your state vector may have a 1 million, 10 million degrees of freedom. Okay, for massive systems, this is very common. I argue that in many systems, what we call quantity of interest are usually very low dimensional. And even for real-world control problem, your decision rarely depends on your solution at every grid point. It depends on some macroscopic quantity like maximum stress, temperature, deformation. And your decision to control the system, usually your control variable, I know distributed control is our thing in math, but in real problem, you don't really control your solution at every grid point. You control, even your fly aircraft, you control this few things. You drive your car, you have a gas, you have a steering wheel, you have just a few degree freedom to make your decision, right? So the overall speaking, this is what we call quantity of interest. They are very low dimensional. In many cases, no matter how massive this is, you're actually dealing with order 1, maybe 10. All right, so basically order 1 number of variables that you really care, that makes your decision. So our idea is that, is it possible, if these quantities are so important, can we just understand its dynamic directly? Instead of solving the whole thing, then evaluate this operator, which is, this is a continuous operator depends on the state for a quantity of interest. With the capital H, I mean on discrete level, right? So this is discrete. Discretized, still very short vector, but depends on full state. The evolution, of course, is not possible because we don't have equation for this V directory. If we do have them, equation for that, you would bet this is already part of the system we have already ordered. So the idea that we ask the question, is there a closed form dynamic system for these few variables? All right, so that has no explicit dependency on the state, because here it absolutely depends on the state. But we would really like to develop a dynamic law for this that depends only on itself, because if we were successful, then to understand the evolution of my quantity of interest, we can bypass the solution of full state. So that potentially can offer a speed up of quite large margin. And this is always done not by standard mathematics. Standard mathematics is to develop all the conservation laws, balance the momentum, everything, but that's already done here, right? So, and this, first and foremost, itself, it doesn't really have a dynamics. The dynamic is determined by the state, which has all the laws, physical laws, mathematical law. This itself is just a function evaluation of this. It follows the state, but we would like to get rid of this dependency. That's our goal. So now we're looking at, I will spend just a few minutes about, this is data-driven part. We're looking at how do we model something we don't know. So how do we model unknown dynamics? We'll start with something very simple. If we have some dynamic system, that all I have is data. I don't have a governing equation. I have time history data. So here's our goal. We would like to create a dynamic model. It's a numerical model. It's not mathematical. Again, if it's mathematical, we would have already derived it, such that the prediction of this can be a good, accurate prediction of the truth. That's the whole thing. So I would argue if you have a governing equation, you would do exactly Runge-Kutta, for example, Olaf for Runge-Kutta, you will get exactly a time step like this. Here we say, I don't have equation, so I don't have that, but we have measurement data. We would like to get to this as well. So without equation, we want to use data to derive this model. All right, so we would like to focus on long-term accuracy, and this can potentially be offered for PD system. In this case, our data would be over time a snapshot of solution. Right? So this is the idea. So we start with a very simple thing. So forget about quantity of interest. What if I can observe all the state variables? I mean, so underlying, there is a governing equation. Let's assume it's an autonomous system. I can observe all the state, but I don't know the equation. Right? So I cannot derive a model like that, but I have measurement data. So that's very simple. For autonomous system, we would just say that the solutions are separated by a mapping. This is what's so-called flow. That's why we call this method flow map learning, FML. The mapping is parameterized by time step. I just assume it's constant time step, which is a restriction, but not so bad for most cases. And this is a mapping. I look at the map state from one state to another. It's nothing but a function, RD to RD mapping. So if I look at this, data, I can put these 2 points out. This is the input, this is the output. From time history, I can have many, many of such little one-step mapping, and then I turn this around into a least square problem. So we don't know this mapping because it's determined by the governing equation. Let's find a parameterized approximation, also RD to RD, such that I minimize this loss. This is nothing but a least square problem. If you over-parameterize it, your data is so large, more than your number of parameters. But how do you parameterize this RD? It's a function approximation. How do you parameterize this? You can do polynomial, Gaussian process, radial basis. They're all linear approximation, in which case this is exactly a linear regression problem. But if you don't, if you so decide that I want to use neural network, you just turn this into a nonlinear regression problem. But nevertheless, there are well-developed tools. You all know TensorFlow with Adam, all these stochastic gradient descent method that can solve this. And with linear regression, there's even larger number of more tools to solve that. So once you collect all these data pairs, you solve this minimization problem, you have fixed this operator, then you get approximated operator like this. So hopefully it's accurate enough. Now you have a time stepper. Given initial condition, you can march forward in time to predict the future. There's nothing fancy here. We did this in this. It works very well. I do say that unless your dimension is very high, if you have low dimension, reasonable dimension, please just do this standard method. They are so accurate. There's no need to do neural network unless you have no other ways. We use neural network simply because in many cases, the dimension of X is very high. We have no other ways of doing high dimensional regression. We just use Adam method. So basically just TensorFlow or PyTorch to do that. Right? So that's all well developed, but let's make things a little more interesting to lead to what I discussed. How do we model some quantitative interest, right? So now we still have measurement data, but I don't know the governing equation. I don't know. But even for this time history data, I know that in practice it's very hard to measure every state variable. Let's assume we're not seeing many of them. So we're going to separate the state variable into part we observe, which is the part we have time history, and the rest of we have no idea. We may know the total dimension of the unknown system, and in many cases, we don't even know this. We don't even know the dimensionality. My ultimate example is weather. Nobody knows the true mathematical model for the weather model, how many variables, maybe there are 10 million variables. But you do observe a few things. The rest, we have no clue. They may not exist. We have, or you know have something, you don't have data. Doesn't matter, let's pretend we have no idea what they are. We look at the things we have data. We ask the question, is it possible? We split this, we call this observable. So you observe part of the system, and you are missing everything else. We ask the question, is it possible to come up with a model that predict your observable only, that doesn't require knowledge of things we don't know? Right? So turns out there's a so-called Morris-Zwangsky formula that does exactly that, says that there is formulation to predict the observables. It depends on Markovian term, depends on the memory kernel, and the memory is infinitely long. The little s goes all the way from 0 to t. T is current time, so the integral is all the way from the initial condition to here, and then some noisy term which models the initial condition. Right? So this is the Markovian Morris-Zwangsky formula. And we use this as a motivation to say, you know what, this memory thing, no system has infinite memory. Right? So in order to understand the state evolution at the current time, I don't need to backtrack everything from the beginning of the universe. It doesn't really matter. What matters are the immediate history. So I would only need to do this dummy variable integral from current time, backtrack to some finite memory. So we change it into finite integral, and then you can do some kind of discretization. At the end of the day, you say, but the biggest thing is that I don't know this Markovian term, I don't know this memory term, and in fact, Morris-Zwangsky says nothing of this. He just said this thing exists. It's an active research field to try to study what the memory kernel should be. Assuming you know the true equation. Here we don't even know the true equation, so there's no way to derive that. But doesn't matter. All we say is that if I put a bunch of stencil in between here, I can say in order to if Tn is my current time, in order to predict the future, all I need is to know something from the current time, then backtrack a few things in my finite memory term. Such thing exists. That's all we ask. All we say. This is our very sort of approximation of Morris-Zwangsky, and this becomes unknown function. Why is it unknown function? Because it's much higher dimension. I say in order to know the future, I need to know the current state and some state in the immediate past, immediate memory, and the input is just become higher dimensional depending on how many terms you have here, depending on the dimension of the observables, which is D, and map to the D. So it's a higher dimensional function map. Doesn't matter, but mathematically speaking, if you have enough measurement data here, we can put enough input here, put an output here to find this map to minimize another regression problem, linear or nonlinear. In this case, nonlinear would be much likely because the dimension goes a lot higher. All right, so I'll give you an example. If you have tested system, you know that in order to predict the future, you have to know two steps in the memory. Now this gives you a 3-to-1 map. Then when you pull your time history data, you better at least have 4 entries. You put a 3 in your input and 1 in the output. And you do a lot of this from your time history to get these 4 pairs, and you can try to solve this problem. Right? So the little caveat is that this isn't really a 3-to-1 map. Your state, the variables you observe can be, let's say, 10 dimensions, so this literally is 30 to 10 dimensional map, and this is where we actually have to use a neural network or this other method to do, because there's no way I can do polynomial of 30 dimensions to 10 dimensions. It's just harder to do.
So, but the W dimension, the W components are gone from there, right?
Yeah, they're gone. Yeah. We don't know them.
Focus on the ones
we know. We only focus on things we know. Right? So that's the whole idea behind what we call this flow map learning, and this we have discussed this. We have many examples I'll show you in a moment. But before we go on, we want to put this a little step further, like make this slightly more general. Now, let's just say you have a dynamic system. Now I put this in a notation more or less like control, but we don't have real control here. I have a dynamic system, autonomous. I have we just call this observable, B, all right? That depends on this. And we ask the question, so observable, now we extend this. You can say, I want to take the average linear operator here, B. I take the average of all the state, or I can say, I take some component, in which case is what I just discussed as Morris-Zwanzig. If it put the E vector here, this will, after applying B, you would simply take UK out of the whole vector. Or you can say, I want to know the energy, 2 norm, or maximum norm, in which case your B is a very much nonlinear operator. So we ask the question, really we're going to call this observable closure problem. Does the Y observable satisfy a closed dynamic evolution law that depends only on itself, not on the state U? Right, so I want to emphasize this is different from what you are maybe familiar with. Since I discussed memory, many people will say, what about Tarkin's embedding theorem? Or this, the common thing like here, Enrique would know, inside-out observability, right? So controllability thing. The biggest assumption here, we do not assume B, this operator, is injective. So it can be totally non-informative. For example, if I want to see the average of my state, well, there are many, many states U would give me the same average, or the 2 norm, for example. Yes?
I don't know when did Mori and Zwanzig write this down. I didn't know this.
Okay.
Could you comment on when?
1950s. Yeah, there are 2 papers I can show you. Yeah. Okay. So this is the biggest assumption. We see B is non-informative. It's non-injective. So there are many, many states U can give you the same Y. We just want, and also we do not try to reconstruct the state. So this is not like this. We're not trying to reconstruct the state, so we don't require. So even if it be non-informed, it's fine. We just want to predict Y based on Y. That's all we did. So there's a fundamental difference in this assumption. That's why Tarkin embedding really doesn't, it's not the same setting. So we have a very practical way. This, you get some Y, I want to understand Y, that's it. We don't care how many U's give us the same Y. All right, so we'll start with linear system because that, of course, right? So let's say we have a linear system now. It's a linear dynamic system. My B is a linear, maybe more than one observables is a linear thing. Again, this can be the average, can be selecting a few components, a few other things. You can do a very simple thing. Turns out this, you can just look at the Krylov space. So I look at this B matrix. So Y obviously follows this system. Again, the dynamic Y follows U. That's obvious, right? But this B of AK, all the Y's derivative follows B to the AK. Now, if we focus on B to the AK, in fact, I do the transpose because it will come in handy. It's a little mathematical thing. It doesn't do anything special. I look at the Krylov space of this transpose B to the AK to B. I mean, B is dimension of M, N is fixed. So this space doesn't grow infinite. I can take infinite number of power of A here. I can write down, but doesn't matter. At the end of the day, this thing is confined by Rn dimension. There's no way around. So based on this, we know then there is somewhere, as you keep doing this, you are not increasing the rank of your space. Your space stays finite dimensional. There's some R which should lessen this. At some point, your dimension, in the worst case, this goes n dimension, doesn't matter how many k you do, right? It's the power you do. So that's a finite dimension. And then you do a little manipulation, you'll find out, because of that, your observable Y follows exactly a linear ODE of R2 plus 1's order. Like it's a linear ODE, C are the coefficients of constants. All right, so this is very much related, if you know, I'm sure many of you, Cayley-Hamilton's theorem, which guarantee this exists for N. But here we say the property of this matrix will stop much, much earlier than N. In fact, much, much earlier than N. So if you have your system of N, 1 million by 1 million matrix, you have some observable. This would follow very low order ODE, not 1 million degrees. But Cayley-Hamilton said that 1 million degree ODE exists. All right. So following this, you can do a little manipulation. You just say, because the linear system equation is finite dimensional, then I say that if this space is finite dimension of R, dimension is R, then that linear ODE would turn around, tells me that the dynamics of observable follows such equation that depends on finite number of delay. That's exactly R plus 1 delay. And the coefficients here are distinct. Whatever delay you have, the coefficients are unique. There's no approximation here. It just says, now in this linear setting, your observable will follow a delay differential equation. You can do this in a continuous form. You can say this is discrete form, which is minimal. The delay is R plus 1 the coefficients are unique. But you can say, okay, I can make this slightly more general. I can write down this as an operator such that my dynamics y follows a delay differential equation, depends on everything from immediate past. In here, the memory can be infinite short, but it's non-zero. I mean, as long as it's non-zero, it's infinite dimension. All we hear is just it needs finite dimension. This, in fact, you can solve for finite dimension. The delay solution at this delay, they become a basis. That's exactly how you can express this. All right, so this is for scalar observable.
So sorry, so in this kind of theorems, what you try to establish is the possibility that the signal you are interested, this goal y, behaves according to an equation of this form, in which all other variables are gone.
Are gone, exactly, yeah.
But for this, of course, you need to know the weight W or the delay density or measure mu, right?
Yeah, tau here,
the tau and the W, right?
Right.
Those are important. And then,
tau, yeah, so.
And then in the second one, it will be the H and the mu, right?
Yes, this is more continuous forms as it exists, yeah. So more practical one is that if you decide the delay, the W is unique, you try to find it, that's all. That's exactly how we trained the thing earlier. We actually, in fact, we did, for linear system, we overdid. These are constant, we don't need, so anyway.
But determining the taux, this is delicate, right? Because this is a nonlinear approximation issue, right?
They are.
Maybe the W's is easier, right? The weight, but the taux is probably, the delays is very delicate.
This is an open issue. You can put, so yeah, exactly. So I have no answer to that. Right. To decide a good delay, that's some immediate open issue we want to discuss. This result as new as 3 weeks. Okay, yeah. So then if I put this slightly more general to vector, if I have more than one observable, this B, then the same result holds with a slight difference that here we don't have this representation is not minimal. I just say there exists a thing, and so it's a slight for scalar thing. The equation is absolute minimal. For the scalar part, it's more the existence. We say that exists an integer such that we have this many, at least this many delay. It can be more. So the derivation here isn't, even though it looks similar, isn't as tight as a scalar case, which is something we're still trying to tighten as of this moment. Anyway, so this is all fine and dandy for linear system. Basically says the observable does follow by itself a dynamic system, but only depends on its history. It doesn't care about state anymore. As long as you know enough history, you can predict the future. Right? So the question is, of course, what about nonlinear system? Then everything breaks down. Okay, so which is not very surprising, but we still try to maybe narrow things in certain things we want to say things. But let's look at the continuous level. Now everything is nonlinear. B is nonlinear operator. All right, so you can formally just take a derivative y, you will follow this. This is what they call the Lie derivative. Okay, so which is exactly that follows on the flow of u. All right, so there's nothing fancy here. Once again, this thing depends on the state, which is not what we want to get, but mathematically this is what it is. We want to ask the question that given enough history of y, can I in a history? I'm going to put current time as 0. Okay, everything before 0 is a history. Everything after 0 is what we want to predict. I want to make a slight difference that I know the history after point 0, including 0. But I want to predict the future, which what's important is the right derivative of y dot, not the left one. Here's the thing, things may not be as continuous as you want. So we want to distinguish the left derivative, right derivative. So if you know the history here, you actually know all the derivative up to the left 0, but you don't know this. Why? Because the right derivative is determined by your state, not by your history. Based on this history, you can take any derivative, you can know the left derivative, but the right derivative depends on the u at this point, and u may change without your knowledge of whatever happened in the past. I'll give you one example, very simple one. We all know Berger's equation. You look at inviscid Berger's equation. I say, you know, my observable, I want to know is 2 norm, the energy, integrated in the 2-part periodic domain. You say, well, this conserved energy. My energy is a constant. So if you have this, you know all your derivatives equals 0 up to the left derivative. But we know if I give you a different state of u, I'll give you 2 states, one is sine fx, and you know at some point And in particular, in this case, at t equals 1, there's a shock. When shock occurs, it starts to dissipate, so your energy will decay. So your history data tells you everything about zero change in your energy to norm, but that's always happened to your left derivative. And right at this point, your right derivative starts to go down. You have no idea to predict based on history because it's you determined it. That's really what happens in nonlinear system. But this impact can be, we try to minimize. Why? Because there are two things here. Braggs equation, if I write it in this form, is infinite dimensional. It's a PD continuous form. Secondly, it's nonlinear, so things may happen. If we make things a little restrictive, maybe we can say something. So that's why we have to, again, nothing we can do, and let's make a little assumption. We make this definition, we call this diminishing ambiguity. Basically says, if I know enough history, that I have two history that's identical for certain memory term in the past, then its immediate future, the ambiguity, the difference in the derivative dynamics are exponentially small. They are bounded. Where there exists such constants such that the longer you observe your history are matching, then the less uncertainty, less deviation it might happen in the future. We think that's a reasonable assumption. We can do that, right? So, and if that holds, if this is... That doesn't apply to the stock market, which is more complex. So that's our defense. All right. So
because stock markets usually, at least nowadays, are very non-in-equilibrium, and these kind of concepts only work with stationary systems.
That's also true. The stock market has external input. It's non-autonomous system. So that's so. Yeah, exactly. Yeah.
Typically, it's not stationary.
So there are many excuses to say it doesn't work for stock market. So. Anyway, so under this assumption, then we can say that mathematically, that does your prediction of the future, you have a closed system, but that would depend on infinite this thing. Then there's no ambiguity. If you history matching only for finite history, then there exists some operator that you have some uncertainty there. There's some, you can quantify this error. But I do say, if you know in many systems, your solution state is C1, which is very often, right? So because for this solution to exist, you require A to be leafage continuous, and then your solution is automatically C1. If you know your solution is C1, then your B is also C1 function, which L2 function is, and then there's no ambiguity because but this is based on that your solution is already C1. You know the state, there's no surprises. So this doesn't apply to Braggs equation. Right? So, but in many cases, this is the case, and then you can safely predict the future. So I think that's, in some way, we try to reduce we try to increase a little bit region where we can predict the future, right? So anyway, this is what I said. So let me show you a few examples. So we start with we did a while ago with linear system. Again, we came up with a randomized fixed number, arbitrary number, such that the system doesn't blow up or decay to zero, which is sort of not very interesting. All right, so we have this 20-dimensional system with all these 400 parameters. We're going to assume we don't know anything about the 10 variables. All we observe are these first 10 components. In fact, we don't even know any of these coefficients here, right? So this is more Riemannian in the sense that we only observe your operator is selection of the first 10 components. We want to predict Z only. Again, the W would have no idea of what they are. So this case allows us to write down exactly more Riemannian, but if we know the matrix term, we pretend we don't. Well, it's a learning method. But anyway, so we conduct learning. So this would be the component, would be first component. Z would be the first 10 components. And you do some neural network with finite number of memory terms with some time delta t. And this is interesting. So our memory term would have 30 steps in the memory, but each memory term, the vector is 10 components. So this is the mapping from 300 dimension to the 10 dimension mapping. So we connect with some simple fully connected network in between to accomplish this 300 dimensional 10 dimension function approximation. There's nothing fancy here. So this is after learning very short memory to generate data. There are two curves here, this by the neural network thing, and this is true values. This is x3 and x6. They all look for I want to see this very long-term prediction for up to 150, much, much longer than our observation data with 0.6, a non-dimensional time. You can do this interestingly, people love to do this for nonlinear chaotic system. We did this with Lorentz. Interesting case that we're going to assume that I don't know the dimension of Lorentz, but I see x and y. That's all we see. And we're going to create the data with x and y to come up with more or less a two-dimensional chaotic system that produce this interesting thing. And this is the true three-dimensional solution projected on the x and y plane. You can see they visually look similar. You look at this few parameter to measure how chaotic the system is, and they look reasonably similar. This is, again, memory is very short. The training data is just pieces of the trajectory of 0.1, and this is a prediction up to 100. It's a very long time prediction. And this is very easy to train. In fact, this is a lot easier to learn than the determinant system I just showed you, because for determinant system for like this, we want to get a very accurate result for long-term point-wise accuracy. Chaotic system, nobody cares about point-wise accuracy, nothing. So in fact, this is easy. One training is done. Anyway, we can do this high-dimensional Lorentz 96, which has 40 dimension state vector, but we pretend we only have data for 1, 2, 3. We train a three-dimensional network to give you this messy, whatever phase portrait, which is similar to the 40 dimension of the first dimension of the true 40 dimension. You look at the histogram of the three component after they stabilize. You get this sort of invariant measure. The color of two different things, they are more or less matched. All right. We do this with Berger's equation to predict this and some other thing. I don't want to spend too much time. I want to come to this example because for this, we want to also do a little bit of control with this. Right? So this is CFD example. I have a standard incompressible Navier-Stokes equation with some Reynolds number, and we can call this our digital twin. And at different Reynolds number, solutions behave differently. At a low Reynolds number, which you can think of lower velocity. For people who are not familiar with this, so the flow is coming from left to right with constant velocity, and the flow, there's a little cylinder here. So this is zoom in the view of this. You have the standard Kalman vortex shedding at low Reynolds number, which is you can think of flow coming slower. You have the standard shedding. A higher speed, high Reynolds number, this become more violent. If you increase the Reynolds number, this eventually become turbulence.
So and it was observed by von Karman, or who was the first?
People observed for a long time. Karman, I think the first named it. That's why it's called Karman vortex. All right. For us, we didn't write the software. We use a freely available software called Nectar++. After discretization, we have about 150,000 degree freedom. So if I put in this context, we have a dynamic system about 150,000 degrees. So any kind. Now we would argue in this case, things we care for flow structure interaction for most practitioners, they care about
where is the motion coming from? There is an initial datum which is.
So the flow coming from left to right is all steady here. Nothing is moving.
So but then is on the initial datum, right? So you are putting. Otherwise the solution will be zero, right? There has to be.
Yeah, the flow comes from here. Is one from here. Then flows here, right?
Through the boundary condition.
Yeah, through the boundary condition. It's all 1, 0, 1, 0 here. Then flow comes in, start to establish itself, yes. And goes to the right, goes out of the domain. So, all right, so we argue that the quantity of interest for decision making is the force on the structure. So we care. The force here, there are two forces. Basically, force is a two-dimensional vector. We look at the horizontal force, and which is called drag, and the vertical force, which is called lift. That's how people in airplane, they care about this. How do you compute the force? It's defined by a stress tensor along the surface of this little cylinder. So, and this definition here, again, the software gives us this. So at the end of the day, you do all this simulation to get two numbers, the force on this, drag and lift. So our quantity of interest here is two-dimensional. So we have a 150,000 degree system to solve, which is very expensive, but all we care is the two-dimensional thing. And there's no shock here, there's no turbulence here, so everything is smooth. We can be very safe to say that we can use history to predict the future. So that's exactly what we're going to do. We want to use the history of this force to predict the force without solving the flow, without the most expensive part. So that's how we do it. So we're going to, this is the offline training, all right? Offline, like reduce all the modeling, everything you do the offline training. How do you do it? We do this many simulations. We first in this Reynolds number with different coming velocity. We sample this. We conduct one simulation, which costs about 2 hours, and full simulation. We're going to record the force of the 2 simulations and then throw away. There's nothing we can save. We only save this. And we do this, the force, and we're going to sample this, and then we repeat this process 7,800 times. All right, so I'm going to show you why I say we have 10 times. 7,800 times later, we have 78,000 pieces of training data. We'll show you in a moment why this is the case. Okay, but this is altogether took us about 4 weeks to do that. Right, so this one simulation, this one sample to renal sample, which again, how far the flow coming, and you can see this lift and drag. At the beginning, nothing happened. You start to develop and then become periodic shedding. You can see this. And this one simulation took out 2 hours. The time is from 0 to 200. So the box here stands for a random sample of 5-second segment, because we have tested 5 seconds is enough in our history. So this by trial and error. We started 1 second, 2 seconds, 3 seconds, 4 seconds, and then the results start to stabilize. We stop at 5 seconds. We don't want to go too longer memory, because the competition becomes more and more expensive. So this is 10 random sample of this segment. I'm going to show you that's exactly how these 10 boxes shows up. Right? So this is a burst. We call it burst 1 to the 10. Each one comes from some random sample time. Randomization is key. You want to randomize everything. Some time. So what do we do with 2 things? First, this random time, the sampling time, we're going to remove this. Right? So we don't care where they are. So everything is 0 to 5, because we just say time is only matter in the relative term. Secondly, we make things more interesting. We say that, I don't know how fast the flow comes. The renal sample, we're going to remove this. So for every single simulation, we're going to record 10 pieces of this training data. We don't know how fast the flow comes. We don't know each one corresponds to what time. That's all we have. Then we repeat. Then we can do this for another simulation. This at a much higher renal number. The flow is come much higher. You can see the drag and lift. Again, nothing happens at the beginning. Then it becomes much more violent. All right. But anyway, 10 box random sampling. Again, I don't care about it. I'm going to remove the time. I'm going to remove Reynolds number. For this simulation data, we end up with 10 pieces of training data. Repeat it 7,800 times. We got 78,000 of such training data, and we have no idea each one corresponds to what the Reynolds number is, the parameter is. We have no idea what the real time this happens, the 5 seconds. Everything is 0 to 5. All right. Anyway, for this 0 to 5, we put a time step 0.1, so everything of this have 51 points. Put 50 at the input, 1 to the last. So that's we have a mapping from 50 to 1, except it's not. Everyone has 2 vector of 2 drag and lift, so it's really a mapping from 100 to 2. But knowing 50 step history of the drag and lift, the vector of 2, we can predict the next drag and lift. That's exactly what this thing training is standard, Atom, fully connected network, nothing fancy here, no structure. All right, so and once we finish that, we're going to do the simulation in the entire different way. The standard way is that give a Reynolds number, do a simulation. This will give you like drag and lift 2 hours, for example. You solve the entire system. Now we just say, give me a little initial condition of 5 seconds. I'm going to evolve this very little dynamic of 2-dimensional model. I go here directly. How do you get the initial condition? You can get it from real simulation, or you can get it from experimental measurement. Either way is fine, but once you have it to start, you can predict it without solving the flow. The state variable is completely outside this. Right, so let me show you two examples. Again, this is after training dynamic model, that's all we have. It's a 2-dimension with 50 points at input. So this is an initial condition from some simulation. All right? In fact, from a fairly big Reynolds number at time 190, so the flow is very established. It's at the end of it. But you know what? This information is not required in this model. We're going to hide this information. All it requires, let's put all these 50 points, drag and lift into this input. And once you fill this up, you can predict next one. And you predict the next one, you do a moving window in your simulation continues. Right? So this is simulation continued after the dashed line is just after initial condition, it's a simulation continues. The red one is this prediction by this model. The blue circle is the true model. We solve the full stage record in the same condition as validation. You can see the accuracy fairly well. All right? This is long-term simulation, and you can measure the frequency. They are matched to digit by digit of the first four dominant frequency. And the simulation goes so fast, I just always say, look, the simulation of this model goes faster than the movie plays. So, but if I do the full simulation, it will be very expensive. Look, let me give you another initial condition which is more interesting. You can see this drag and lift for 5 seconds. They don't look stable, which is exactly the case. This is at this Reynolds number time equals 1. So the flow just starts. It has not started to develop. It just tried to develop. But
this Reynolds number is considered to be high?
This is, in this test, it's considered to be high. In this, but in real thing, you can do 10, very high to be turbulence. We're not there. We didn't do turbulence. This is only so far demonstration, right? So
what is the order of the Reynolds number when you are talking about commercial airplanes, for instance?
10 to the 6 and 7.
10 to the 6?
Yeah, it's air. This is flow. Liquid is lower Reynolds. So for the typical 10 to the 6, I would say. So again, these conditions are hidden from this model. We're going to feed this thing into this and let this thing develop by itself. You can see that, yes, it hasn't established, but somehow the models start to find where it will go. All right, so eventually it finds its whatever steady state at the end of the day, especially for drag to find a different state. And again, the accuracy comparison is very, very fairly good for this long-term prediction. Right? So again, the history, the memory is only 5 seconds, and this is prediction up to 100. Anyway, so
49 number, do you expect it to be related to the Reynolds number or not?
In this case, no. If
so you don't need more memory when the system is more unstable?
If you say that we did range 100, Reynolds number 100 to 2,000. In this range, this is, covers everything. If you say I go to 10,000, I don't know. Probably. In fact, probably less, I would say. The more chaotic, the less memory. It goes counterintuitive. Yeah. It's the deterministic problem that has longer memory. It's a chaotic thing they just quickly forget. Yeah. Yes?
I kind of disagree with that statement because...
What statement?
This is essentially almost an oscillator. And from the spectrum that you were showing, it looks like you have very few dominant frequencies.
Yeah.
And this is kind of a situation where you could use with these embeddings, I know you said it's kind of different from Tachen's embedding, but it doesn't seem too unrelated. And a linear system with enough delays will replicate exactly a periodic system. Now, the higher the Reynolds number, the more characteristic frequencies you will have, and that's what I would imagine the longer, the more delays you will need to capture it. So it's actually not too surprising that in this weakly chaotic regime, you do quite well.
You mean?
Well, this theory that tells you that a time delay system, a linear time delay system, will capture a periodic signal exactly given enough delays.
So there are two things. I think I alluded to this earlier. This is in Tachen's embedding is not applicable here. Tachen's embedding requires your history embeds the state. Here, this is drag lift. It doesn't embed state. The state is 150,000 or whatever, 1 million. I can discretize as high as I want. But these are two numbers. So this is complete outside Tachen embedding theorem regime. So secondly, if you say you disagree with the memory is higher or lower at the higher Reynolds number, I couldn't see anything. Nobody tested this. Nobody has ever done this. I don't know the memory if it's become...
So I've spoken to a lot of fluid dynamicists in the past, and they said that whenever anyone tries to do any data-driven modeling, not just anything...
I understand. I understand. Nothing works in turbulence. Nothing works in turbulence. Okay? We agree on that. I also understand, I'm very familiar with data-driven modeling. Nobody has done this with fluid, so I cannot say either way. What I said in turbulence, maybe memory short is complete speculation based on my own experience of modeling many different systems, which I think I'm 60% possibly correct. But I'm very open. It could be longer memory, but I do think from all the things, determinisms we have tried, the more chaotic it gets, the actual shorter memory it gets. But any system is different. And also, turbulence is a completely different animal. So could be surprises there. It happens all the time. All right, so anyway, so let me show you a different quantity of interest. Let me say that In this case, I want to understand the pressure distribution along the surface of a cylinder, which is in many cases, people make a decision on that, right? So where the higher pressure is. In this case, it's not just two numbers. We're going to model a function along the surface. Luckily, the cylinder is a periodic function, so I can write this surface function representation in the Fourier series. I can just track the coefficient, which is fine. We're going to use memory to learn that again. So this will be the learning. So the memory same here is the same. Let me let this thing go first. This Reynolds number, so we learned enough. It's the same 5-second memory of surface pressure. So this is surface pressure. I'm going to say flow coming from left and right. The diamond is the front. So that's where this 0 to 2 pi slide is open. This is the diamond, the front. And the blue circle is the back, the real part. So the flow coming from here, higher pressure is here, lower pressure is here. The entire distribution would be like 0 to 2 pi, plus minus pi like this. So 5-second learning, this is prediction up to t equals 500. In fact, let me not play this video. You can see the prediction of this small model, again, goes way faster than this movie, and the reference of whole CFD simulation. But anyway, this is too long because let me put to the end. You see the interesting, again, no method would be immune to long-term error accumulation. This as well. You can see the error accumulates at the end. They're not too bad. They still capture the shape. There really is the phase difference. Again, this is 500, I caution. Such long-term integration, I think this phase error is actually quite small. We don't have error analysis because deep down it's a neural network, prevents us to do any concrete, meaningful mathematical and numerical analysis. So finally, let me finish this with the flow control problem. All right, so this is the same flow path cylinder. And there are people who try to do drag reduction. There are many different ways to try to do drag reduction. We're not proposing any new ways of doing this. We found this way from one of JFM paper. I forgot the reference. I apologize to the authors. Anyway, that introduced a little jet on the side of the cylinder. Open up about 10 degrees. In fact, we did 9 degrees, slightly different. The jet profile is parabolic profile. We control the maximum of the jets. And the jets can go plus, minus. When it's minus, goes in. So it's a blow and suction. They go opposite direction to make sure zero mass is introduced in the domain. So we're going to control this maximum suction or blow from +1 or -1 every 0.1 second. The goal is to minimize this cost function. Again, this is from the reference, which is the average of the drag over 5 seconds and plus a regularization of something with the absolute value of the lift.
So then, sorry, what is this then? You cut and then you let fluid getting into the
Yes. So numerically speaking, all I have is a time-dependent directional boundary condition at the side of the cylinder. Okay. A very teeny opening. We have about 10 grid points. We have a time-dependent boundary condition here to change this. That's all.
This is kind of open loop.
Here it's closed loop.
Boundary condition will be open loop or closed loop?
Closed loop. Yeah. So it's a feedback control. Yeah. So it's so now we have to get a new model. The new model that depends on history of drag and lift, but also depends on the control signal, which is that boundary condition. What we do to generate offline training, we do RID, randomization. We train a model, and with history, we have this. So now we're going to put this into a control loop. There's nothing, it's a busy slide, but there's absolutely nothing from us. All these things are standard. Reinforced learning, just our method allows us to, reinforced learning by itself is offline training. It just keeps playing different scenario and fix your reward function, get a better policy. And this allows us to do about 1 million scenarios because this model goes so fast. Right? So if we do the CFD thing, we estimated we had to accomplish the whole thing in about 5 months, which we didn't have appetite doing that. Model predict control is very straightforward. Just predict a few steps, do the standard optimization, then take the immediate next step as your optimal solution. And this you do the standard, gradient descent, all these things, they're very similar things. So anyway, we'll do this in real time because the optimization. So let me put everything together. It's the feedback control. Now it's on the fly. We're going to run the simulation in real time. As the simulation goes, the simulation will produce us a little history of drag lift, and we use our little model to train the control signal. The signal would be feedback as a boundary condition in here, and then that's the entire control loop. And this happened on the fly because for CFD solver, we only need every 0.1, which on the this simulation, about 15 physical seconds, we need a new signal, but these two controls give us this thing so fast, there's no need to wait, right? So everything happens in real time, the control get updated, so let me just finish this. Just for reference, if you're fluid dynamic, you will find this interesting. There's a little side thing here, it will change the vorticity, but anyway, let me show you this, the end result. I mean, this is more interesting. So anyway, this is over time, and this is uncontrolled case, which there's nothing here. You take average, almost the drag is almost constant. But now with the active control on the fly, this is the red one is by model predict MPC, the blue one is by PPO, by reinforced learning. You can see that there's significant reduction in drag. Again, we're not proposing the best reduction. We follow exactly what's in the literature, but this is what we accomplished, about 20 to 30% drag reduction. This is a real number. There's no application because the drag is computed by the high-resolution CFD solver. All we did is using these two to give it a different boundary condition in real time on the surface of the cylinder. This is the drag lift computed by the full solver. So, all right, anyway, so I hope I have introduced you to this sort of newer class of data-driven modeling technique, but I want to emphasize it's a sort of newer mathematical question. Is that when does the observable have a closed form representation? And even for the linear system, how should I place the delay? What's the condition number? What's the numerical analysis? Everything is wide open. Really, this is, if anybody has some idea, all these things we did are completely numerical. Up until, I forgot the news reference 3 weeks ago, we have the theory, the delay representation we showed earlier. So I forgot that thing, actually. Anyway, so with this, I finished. I thank you for your attention.
Thank you. Thank you. Great talk. Thank you. Questions or comments? Please go ahead. Please go ahead. You can start. Okay.
Since I see here a comment on stochastic differential equations, could you briefly comment on this?
Yes, so we have done some stochastic differential equation that requires us to do the similar thing, but it has to be a generated model. So it means that the model has to generate randomness. So we have used the flow map, just one-step mapping. Mostly it's for fully observed system. There's no...
There's also a concept of flows of solutions of stochastic differential equations.
That's true, yeah. So,
a long time ago, 50 years.
yeah, so we have not done anything of that, but we just numerically, we have shown that you can do model unknown stochastic system with the more or less standard technique many students probably have heard. We started with the GANs, which is a fascinating mathematical thing, but which is extraordinarily difficult to train. I mean, I started as my favorite thing. After that paper, it's my least favorite thing. So normalizing flow or diffusion model, both are fantastic. But they don't work as good as GANs in high dimension. So we have tried all this. This is why there's few papers. We also tried autoencoder, decoder. In fact, these 4 papers are exact 3 different approaches. So anyway, so we have done some early works. But for partially observable dynamic for SDE, we have nothing there yet. Nothing, either mathematically or numerically. Yeah.
And I understand that you did not pass the Reynolds number to the network.
Yeah.
So you passed only the 50 values.
Yeah.
Which is, I mean, a bit surprising to me. So basically the model is able to understand that the history of these 2 variables, like if I understand correctly, the dependence on the Reynolds number, so it's completely encoded in the model.
In the history.
In the history.
Yes.
Yeah.
Yeah, so it's interesting to ask. In fact, many people ask, we could have the Reynolds number as an explicit parameter, save it and train. We didn't do that. Simply, we want to make this a little more fancier. So we have many other things. We have some parameter we explicitly feed the model, and the rest are hidden from it. The flow things, they happen just be one Reynolds number, so which is, it was a decision which, let's hide it so that it looks fancy that the thing can predict it even without knowing the Reynolds number. But the information about everything that's missing, the flow, the Reynolds number, is sort of hidden, embedded in the history. So somehow,
There cannot be two equal histories with different training.
that's up to the little theorem. Even if there's a two thing that deviation is very small, you don't see it. Okay. Which also means if your history is too short, you're not going to predict. You want this long enough so that it becomes more or less unique. Yeah.
Okay. And the second question was, well, very standard for this type of works. You introduce a model which is obviously very interesting because it's connected also to the physics, right, of the equation. But this idea of dynamical systems with memory in machine learning is already used, for example, by LSTMs, recurrent neural networks, and so on.
Yeah, yes.
And I wanted to know if you made some comparison with.
So when we first did this, one question we often get is, why don't you use any structure? And people say LSTM. We tried that, in fact. It will work similar way. It will accomplish. So my answer usually is, why should we use a different structure? Right. Because, like I said, what I didn't have, this is exactly what I meant, that this capability have nothing to do with neural network. It's all about understanding mathematics. You're mapping from something to something, because at the end of the day, whatever structure is a mapping from what dimension to another dimension. Once you understand this mapping, is there anything special within the mapping that I need structure? We have not found. So that's why we keep using fully connected network. There's absolutely no need to do fancy structure. Not that everything works in one shot. We always, at the beginning, things didn't work well. Then we look into everything. It's all about training data setting. It was never the structure. So we never had a need to use LSTM. But if you want to do LSTM in this, you can. It will give you similar result. We have tried that.
Thanks for the nice talk. Currently, as far as I understood, you're always prescribing like the reduced space given by this mapping B, for instance, to consider drag and the lift in this fluid system. But of course, maybe another reduced space could be more optimal for identifying the dynamic system in this reduced space. Is there any possibility to like learn such a mapping B?
We did not look into. So this is under the assumption that the quantity of interest is whatever people care. So if they say, I care about this, we're going to try to model this. You're asking a slightly different question. For given states, what are the optimal thing I observe that can maybe short its memory, or even maybe try to reconstruct state? That's, again, entirely different thing. We have not looked into that at all. So, yeah.
Yeah, Giovanni. So building on the last two questions, one is if there's nothing special about the model structure, why not go simpler and use a linear model with time delays? And then maybe the second part of the question is, you said you tried no difference in results, but did you see a difference in how many delays you need depending on what architecture you use?
Okay, so maybe linear mapping, because this is, for if you set up the mapping, the mapping is nonlinear. If you try the linear mapping, which is, single layer, linear activation function, no bias, maybe even with bias, which you just have a fine approximation, it wouldn't get there. You actually, so because the mapping itself, like this, is nonlinear mapping from history to future, so that's why it has to be nonlinear. The other one, what was the other question? Was that, LSTM. We didn't try that harder because LSTM just has so many things to play. There's, the gate and everything, parameters. I mean, like I said, we know the mapping has to be 50 to 2. All I need neural network is basically a functional approximation. If I could do the 50-dimensional polynomial, I would do the polynomial, which will be way more accurate than any of this. So we did not compare that, just like we didn't feel there's a need to compare, just because LSTM is. Like I said, the delay is a system. It determines that math or physics has nothing to do with network. So the delay, like we do analysis, the delay really is a system what you're dealing with, the entire state, you're observable. And once this is, the number of delays is fixed. It's not a network property, which is something we want to distinguish, right? The network doesn't give you anything. My message is that math is more important, so.
And how would that relate to that theoretical results of the left and
So,
the right?
so if you train, there are two things, right? If you train your result on a fixed Reynolds number, which is what we started with, then you cannot predict a different Reynolds number. This is very special with fluid. Other linear system, I can turn the parameter a little bit, the result will be good. Fluid is just very non-forgiving. It's like a reduced order model. You do a POD for Reynolds number 100, it doesn't even work with 105. I'm sure you know that, judging from you asked the question. I'm very familiar with fluid. So that doesn't work. So that's why we cover a range. So in that case, if you change the Reynolds number, it wouldn't work. But if we do what we do, that's in the range, then I have one Reynolds number that's not in training data. Then in between, I change it. So if I can properly restart the memory, it will work. Because once you change the Reynolds number, the memory is slightly different. I have to feed that intermediate thing, I have to feed with the new history. If hopefully from CFD, if you give me that, it will work well. But you ask if the model, this two-dimensional model can transient by itself within Reynolds number. We never tried, I don't think so. But maybe, but I don't think so. I think I'm 70% sure it would not work. But there's always surprises. Maybe this time can be a pleasant surprise, who knows?
Okay, so thank you again
All right.
for
Thank you.
this interesting talk and discussion.